In this video, we're going to go over the Hofmann and the Curtius rearrangement reaction. So let's start with the Hofmann first. So what does this reaction do? The Hofmann reaction converts an amide into an amine with the loss of a carbon atom. The reagents that you need is the halogen, like bromine or chlorine, under alkaline conditions, mixed in water. So what product will we get in this reaction? To draw the product, all you need to do is get rid of the carbonyl group. You take that away and that's going to be your answer. So you're going to have these three carbons along with the NH2 group. So we had 4 carbons to begin with. Now we should have 3. The carbonyl group leaves in the form of CO2. Now under alkaline conditions, CO2 is going to be in the form of carbonate. So you might see the byproduct sodium carbonate. Other products that can be formed are sodium bromide and of course H2O. But let's not focus on that. So let's work on another example. Let's say if we have an amide that looks like this. So using chlorine, sodium hydroxide, and water, what is the major product of this reaction? Once again, all you need to do is just get rid of the carbonyl group and attach these two together. So the product is going to look like this: cyclohexoamine. And so it's relatively easy to draw the major product of the Hofmann reaction. But now how can we propose a mechanism for the conversion of an amide into an amine with a loss of a carbon atom? So let's begin. Let's start with a generic amine. I mean amide, not amine. So the first thing you need to realize is that the hydrogen that is attached to the amide nitrogen is relatively acidic due to the stabilization of the conjugate base. And so we're going to start with hydroxide. And that's why this reaction works well under alkaline or basic conditions. So hydroxide is going to remove the hydrogen. The nitrogen-hydrogen bond is going to break, and those electrons are going to be pulled towards the nitrogen atom, since nitrogen is more electronegative than hydrogen. So at this point, the nitrogen atom is going to have a negative charge. It has 2 lone pairs and a hydrogen attached to it. The oxygen also has 2 lone pairs, but it's neutral. So we can draw the resonance form of this particular conjugate base. So the nitrogen can take a lone pair, form a double bond, causing this pi bond to break. And as you can see, the negative charge is shared between the nitrogen atom and the oxygen atom. And that's why this hydrogen is acidic, or relatively acidic. So this is what we have so far. Now at this point, you can use either this particular resonance form to react with bromine, or you can use this form. Let's do it both ways. Using this resonance form, here's what's going to happen. So we have our Br2 molecule. Each bromine atom has 3 lone pairs. So we can take this lone pair, form a double bond, causing this double bond to attack the bromine atom, which will expel the other one. And so what we're going to get is an N-bromo amide, which will look like this. The bromine atom is going to be attached to the nitrogen atom. Now let's get that same answer using the other mechanism, or using the other resonance form. So starting with this one, we can also show this step using this particular resonance contributor. Now the nitrogen has a negative charge, so it's nucleophilic enough to attack the bromine atom. And as you can see, that's why the bromine atom adds to the nitrogen atom. It bears the negative formal charge. Now what's going to happen next? The next thing that we need to do is we need to use the base hydroxide. Due to the presence of this electron withdrawn group, this hydrogen is going to be more acidic. Anytime you add an electron withdrawn group to an acid, the acid becomes more acidic. So it should be easier to remove this hydrogen. So now the nitrogen has a negative charge once more. And not only is it stabilized by resonance, but it's also stabilized by the inductive electron withdrawn effect of the bromine atom. But let's draw the resonance form. So we're going to take a lone pair, form a double bond, causing this pi bond to break. So the nitrogen now has a double bond. The oxygen has 3 lone pairs, and it bears the negative charge. The nitrogen now only has 1 lone pair. So what's our next step here? So first, let's make some space. Now at this point, you want to pay attention because this molecule is going to rearrange. So the oxygen is going to use one of its lone pairs to form a double bond. Now it can break this pi bond, pushing these 2 electrons back to the nitrogen atom, but if we do that, we're going backwards. Instead, the R group is going to migrate. Now, when the R group leaves, it's going to be nucleophilic. It's going to have a negative partial charge. So as the oxygen forms the pi bond, it's going to cause the R group to leave. But it's not going to leave completely. It's going to migrate towards the nitrogen atom. And the reason why it attacks the nitrogen is because not only does it have this electronegative group, but bromine's a good leaving group. And so the bromine atom will be expelled. So now let's be careful how we're going to draw the product of this step. So the R group is now attached to the nitrogen. The nitrogen is no longer attached to the bromine atom. The bromine atom left. However, the nitrogen is still double bonded to the carbon atom. But the R group is no longer attached to the carbon atom because this bond broke. But the carbon is now double bonded to the oxygen. So this is the structure that we now have. This is known as an isocyanate group. Sometimes your professors may test you on the intermediates of this reaction, so you may need to know this. Now, in the next step, hydroxide is going to act as a nucleophile. The carbon atom is situated between 2 electronegative elements, so this carbon atom has a strong partial positive charge, which means hydroxide is attracted to it. Hydroxide is going to attack a carbon and is going to break one of the pi bonds, particularly the pi bond between the carbon and the oxygen, because oxygen can stabilize a negative charge better than nitrogen can. So we're going to have this intermediate. So here's the OH group. Here's the oxygen that lost a bond. It now has a negative charge. Now in the next step, we're going to take a lone pair, form a double bond, and put a negative charge on the nitrogen. So this intermediate is stabilized by resonance. So what do you think is going to happen next? This should be a single bond instead of a double bond. So this nitrogen has two lone pairs and a negative charge. So what's going to happen now? It's going to act as a base, taking away a hydrogen from water. Our goal is to turn this into an amine, so we need to add two hydrogens to it. So this step is crucial. This is the first hydrogen we're adding to this nitrogen. So the intermediate that we now have is known as a carbamic acid. Not a carboxylic acid, but a carbamic acid with an M. Now that water has lost a hydrogen, we now have hydroxide. It's going to act as a base, and it's going to quickly react with the acid. So it's going to take away a hydrogen from it. So right now we have this intermediate. Now what do you think is going to happen at this point? We're almost done. At this step, we're going to have decarboxylation. The oxygen with the negative charge is going to be used to form a double bond. And then the bond between a carbon and a nitrogen, those electrons will return back to the nitrogen. So what we're going to have is the R group attached to the nitrogen atom. The nitrogen currently has one hydrogen, and because the electrons went on it, it now has two lone pairs and a negative charge. Now this is a very unstable base, and the nitrogen ion is going to quickly grab a hydrogen from water, turning into an amine. So that's the mechanism for the Hofmann rearrangement reaction. Now let's go back to the decarboxylation step, because there's a way in which you can show the mechanism without drawing an unstable nitrogen intermediate. So let's put water in the right location. So as the decarboxylation step is about to take place, as this oxygen forms a double bond, instead of putting this bond on the nitrogen atom, you can use it to grab a hydrogen from water. So this will take it directly into an amine. It's now going to have two hydrogens and a lone pair. So you can avoid an unstable nitrogen ion. Now what about CO2? How does it convert into carbonate? The CO2 that is produced is in the alkaline environment. When you mix CO2 and hydroxide, it's going to turn into carbonate and water. Because one of our products were sodium carbonate. The sodium comes from sodium hydroxide, by the way. So here's carbon dioxide. It has a partial positive charge, and hydroxide is going to act as a nucleophile. It's going to attack the carbon, breaking one of the pi bonds. Now another hydroxide ion is going to take away this hydrogen, producing a water molecule. And so now you have the carbonate ion, which looks like this. And it can pair up with two sodium ions. Now let's go over the Curtius rearrangement reaction. This reaction is similar to the Hofmann rearrangement reaction, but instead of starting with an amide, we're going to start with an acid chloride. In the first step, we're going to add sodium azide, NaN3. In the second step, we're going to add water along with heat. Now, like the Hofmann rearrangement, we're going to lose the carbonyl group. So we're going to have 3 carbons instead of 4 carbons. We started with 4, now we're going to have 3, and then there's going to be an NH2 group on the primary carbon. So this converts acid chlorides into primary amines. Now let's talk about the mechanism of the reaction. But before we do that, go ahead and predict a product of this reaction for the sake of practice. Just to make sure you understand it. So feel free to pause the video and draw the major product. So all you got to do is get rid of this and take away the carbon with it. So on this carbon, add the NH2 group, and this is your answer. So that's the Curtius rearrangement reaction. So let's begin by drawing the acid chloride. In the first step, it's going to react with the azide ion. That's the N3 ion, which looks like this. It's 3 nitrogen atoms connected by means of double bonds. The nitrogen atoms at the end, since they have 2 bonds, they have a negative charge. The one in the middle, which has 4 bonds, has a positive formal charge. So one of the nitrogen atoms will attack the carbonyl carbon since it bears a partial positive charge, breaking the pi bond. So I'm going to put the chlorine atom at the bottom. So this oxygen now has a negative charge, and this is the intermediate that we currently have. So what do you think is going to happen at this point? Once we form this tetrahedral intermediate, the oxygen will take one of its lone pairs, form a double bond, and expel the chlorine leaving group. Chlorine's a good leaving group, so it's going to leave easily. And now we're going to have this particular intermediate. Now what we need to do next is take a lone pair from the nitrogen atom on the right, form a triple bond, causing this double bond to break. So this is just a resonance structure of what we currently have. So now we're going to have a triple bond between these 2 nitrogen atoms. The reason why we want that is because nitrogen gas, N2 with a triple bond, is a very, very good leaving group. So we're going to get rid of this group soon. Now this nitrogen has a negative charge, and that negative charge is stabilized by the oxygen atom as well as this particular nitrogen atom. So the negative charge is shared between the oxygen and these 2 nitrogen atoms. So now we're going to draw the next resonance structure. So what we're going to do is take a lone pair from this nitrogen, form a double bond, causing this pi bond to break. Keep in mind, this nitrogen has a positive formal charge. So what do you think is going to happen at this point? Notice this R group here. Just like in the last example in the Hofmann rearrangement, where this R group rearranged to attack a nitrogen and to kick out the Br leaving group, something similar is going to happen. This oxygen is going to reform a double bond, causing this R group to migrate towards this nitrogen, only because there's a good leaving group on that nitrogen. And so this group is going to leave. let's clear a few things away. So let's think about what we have. The R group is now attached to the nitrogen atom. And this nitrogen is no longer attached to the N2 group. The N2 group left as nitrogen gas, which is very, very stable. So this step is not reversible. Once nitrogen leaves, that's it. Typically, the formation of a gas drives the reaction forward. Now, this nitrogen is still attached to the carbon, and it's double bonded to it. And the carbon is double bonded to the oxygen. So once again, we have an isocyanate intermediate. Now keep in mind the solution is not under basic conditions. It's under neutral conditions. So in a Hofmann rearrangement, we would use hydroxide to attack the carbon. But for the Curtius rearrangement, we need to use water. Now even though water isn't as nucleophilic as hydroxide is, it can still behave as a nucleophile and attack the carbon. So now we're going to have an OH2 group, and we still have the red oxygen, which now has 3 lone pairs. But this oxygen carries a plus charge. So now we're going to use another water molecule to remove a hydrogen. As we do that, this water molecule is going to turn into H2O+, making the solution slightly acidic. Now the next thing that's going to happen is we're going to use the lone pair to form a double bond, pushing this pi bond onto the nitrogen. So this is a resonance structure. Perhaps you can see what's about to happen. So we're going to generate the carbamic acid again. But first, the nitrogen has to grab a hydrogen, in this case from H2O+. Because remember, water, it grabbed a hydrogen, turned into H2O+, making the solution slightly acidic. So water is now in this form. So once nitrogen grabs the hydrogen, the solution will be neutral again. We're going to have water. But now we have the carbamic acid. Now water is basic enough to remove a hydrogen from a carboxylic acid functional group. So water is going to take away this hydrogen. So now we're going to have a deprotonated carbamic acid functional group. So we're going to take the oxygen, use one of its lone pairs to form a double bond, put in a negative charge on nitrogen. And so now this nitrogen has 2 lone pairs and 1 hydrogen, and it has a negative charge. Now the solution is slightly acidic again because water absorbed the hydrogen. So now it's in the form of H2O+, which we can draw it like this if we want to. So the nitrogen with a negative charge will quickly grab a hydrogen. And so now we have our amine. Now keep in mind, just like before, we can show an alternative step if you want to avoid a negative charge on a nitrogen atom when it's not resonance stabilized. Now, if the nitrogen ion were stabilized by resonance, then it's okay to leave the negative charge on it. So we're going to put H2O plus very close to the nitrogen atom. So we can show the last step like this. We can use this oxygen to form a double bond, causing the carbon-nitrogen bond to break, and those electrons will be used to grab a hydrogen from H2O plus, regenerate in water, keeping the solution neutral. So now we have two hydrogens attached to the nitrogen, and there's one lone pair. So that's our R and H2 group. And here, decarboxylation occurred. So we have CO2 in the solution. Now we don't have hydroxide, so carbonate shouldn't form here. When you mix CO2 and water, however, you can get carbonic acid. So this process is reversible. But CO2 is the gas, and if the solution is open to the environment, it can just leave as a gas. But that is it for this video. So now you know the mechanism of the Hofmann rearrangement and the Curtius rearrangement reaction. Thanks for watching.